Uh, uh, Gavin, are you okay?
It's pretty hot over here.
Yeah, I mean it looks like maybe you're not in a super safe place right now. Do you need help?
Yeah, I turned my time machine back a little bit too far, and I'm in the Archean. It's pretty hot.
Wow, okay, but like do you need like everything's okay though?
Everything's good. Yeah, we can go along with the pop up. I'm just up here on this ridge.
Okay. Graham, are you okay? Where are you?
Ooh, it's a little chilly out here. So, Gavin, you see, I think I took a wrong turn back in the Permian and ended up in the Cryogenian, and it's chilly out here, to say the least.
Oh gosh. Yeah, I wish you had a jacket. It looks like you're wearing a t-shirt there. Probably not
Yeah,
the best choice.
I thought I was going to make it back to the Archean with Gavin, but that's all right. The snow's good. I'll get a tan with all this light here, so.
Awesome. Well, yeah, I'm just in 2020 Santa Cruz. It's kind of a dreary day here today, a little foggy, but light layers. Always do light layers in Santa Cruz. Okay, great. Well, it looks like everyone's comfy, whether we are in a fiery pit or like a snowball Earth, or in Santa Cruz. So maybe we should get going with the pop-up. What did you guys have planned for us today?
Yes, let's do it. I'm gonna share my screen. Oh, can you enable
Oh,
my
yes, yes, yes. There you go. Oh, wait, hold on. Yes.
Okay. So we are going to do time again today. But so last week we talked about the actual, like some of the best events or the most important events in Earth's history. Well, today we're going to talk about how we actually date them. So if you remember from last week, we talked about this geologic time scale. And what we said was there's 4.5 billion years of time here. And that's sort of a hard concept to wrap your head around. But we talked about some of the major events, as I said. So we had the Pleistocene and the Ice Ages. Those were pretty recent, about 2.5 million. We had the meteorite impact that killed the dinosaurs at the KPG boundary down here. We then went all the way back to the end of the Permian to talk about the biggest mass extinction in Earth's history, which was the end Permian. We went to Snowball Earth, which Graham is unfortunately stuck in now, all the way back in 720 million years ago. We went to the first life in the Archean, and finally the origin of the Earth with the accretion from the planetary nebula all the way 4.5 billion years ago. But Graham, I think that to allow everyone to wrap their head around this, we can make a better analogy than just the geologic time scale for time, right?
I think that's a great idea, Gavin. And I love how you laid out each of these steps in here, this taking us in an overview through these great points in time we covered. But as wonderful as this time scale is, the layout of it is a little bit deceiving. That column over on the far right, or maybe, yeah, I think it should be the right for all of you, with the Proterozoic and the Archean, that's 3.5 billion years of time wrapped up in there. And the next billion years is the 3 columns over. So when we just look at this, time scale, we'll say it's very Holocene centric. It thinks about, the youngest times, and it doesn't actually give you that good of an idea of just the enormity of the geologic time that stretches out before us. So how can you make it a little bit easier to wrap our minds around, Gavin?
Well, Graham, we're going to do a fun little exercise here. Oh, I'm going to change slides. We're going to do a fun little exercise where we're going to tell geologic time as if it were happening all in one day. So people think about time a lot in days, 24-hour period. So what I've gone and done here is put those events that we talked about last week on a 24-hour clock. So in the first second, we'll say the Earth was formed. That was 4.5 billion years ago. If that's the case, then the first life happened at 4 a.m. So life actually started pretty early in the day. I'd be pretty tired at 4 a.m. And life lasted pretty much the rest of the day. So I think that life is pretty special here on Earth. But then as you can see, and you kind of alluded to this, Graham, pretty much the whole rest of the day, nothing's happening or nothing we covered. So there's not that much in the rock record for the first, 3 billion years of time on Earth. And then, so that means that Snowball Earth, which is still 720 million years ago, that would have happened at around 9-ish or 10-ish p.m. So this snowman here represents Snowball Earth, and so there's a lot of time in between there.
It's already pretty late in the day, and 700 million years ago is no small trip.
That's right. So if we march on, the end of the Permian, that's 250 million years ago. That's up here. Almost already in the 10s, already 10 p.m. when the Permian's happening. And then the dinosaurs are killed off. It's already 11:40 p.m. That would only be 20 minutes ago. So you can see, everybody thinks about the catastrophic meteorite that killed the dinosaurs. That's 60 million years ago in time. But in terms of the whole time scale, that would only be 20 minutes in a full day's worth of time. But it gets even sort of funnier when you think about human time scales, right, Graham? So I put here the human time scales. Can you take us through that?
Absolutely. So at 1 minute to midnight, we fall into the ice ages. The ice ages certainly feel long ago, but those have only been going on for about 2.5 million years. So the Pleistocene just starts at 1159, just after 1159. Humans, Homo sapiens, evolves at 38 seconds before midnight. And then if we're going to go all the way to the Holocene, these last 10,000 years in which we've seen the rise of human civilizations, that's all happening in 0.2 seconds, in 0.2 of a second before midnight. So it really is, almost imperceptible, the time that we're familiar with when it's happening compared to the age of the Earth.
Really puts it into perspective, Graham. So I have a question for you. We have these events on a timeline, but how do we know about the timeline itself?
That's a really good question, Gavin. And this is one that geologists for all of the time folks have been studying geology since Hutton looked out at Sicker Point. We're wondering how they could keep track of that all, how they can compare the ages of things. And geologists use two techniques. And one of them should be one that most folks are already kind of familiar with. We talked about the law of superposition when we were talking about sedimentary rocks, and that's just a fancy word to say that when things are getting laid down as layers, the older layer is going to be beneath the younger layers. And so that is the way that we can date relatively. We're not saying exactly how old something is, but we're saying that this rock, because it formed beneath this rock, is older. There's a couple of exceptions to this, but at least when we're talking about sedimentary rocks, this is something we can really rely on. And what's another way we can keep track of relative time, Gavin?
Well, Graham, so geologists and paleontologists for a very long time have also been using fossils, and that's why I have a picture of a fossil here. And fossils that are really useful for time are called index fossils, and the reason they're called index fossils is because we know that they're happening in a relatively short period in Earth's history, but that we can think about it, that they're happening in a specific time in Earth's history. That way, if I find this fossil and I know when that organism lived, I can look at that rock and know that since it contains that fossil, it must be around this amount of time. So I'm not putting an exact date on it, not an absolute date, but it's a relative date based on the organism I know is in there.
That's great. So if I were to find a dinosaur bone in a rock, I would know that that rock probably formed sometime between 250 and 60 million years ago.
That's right.
That's a pretty generous time frame, but we know it's not Archean, and we definitely know it's not occurring, in the Holocene. So those can still be helpful restrictions. And so you mentioned that there's ways that we can date relatively, but then there's ways that we can date absolutely. So what do we mean when we say an absolute date?
Well, Graham, this is a date that we measure based on something that's quantitative, that we could put an exact number on that rock. So it's based off a measurement, and we can say that that is within some uncertainty exactly the age that we get from that date.
Oh, that's great. So it's not just like saying that like Graham is older than his younger brother, but it's saying that, oh, Graham is 28 and his younger brother is, oh, how old is my younger brother? Oh, he's 24.
Exactly. That's exactly right. And so, Graham, I have a couple of pictures here. And the first one is of an atom. And that's because absolute dating is based upon the measurement, almost always, is based upon the measurement of atoms. And these kind of atoms are the ones that decay. They're called radioactive atoms or radioactive elements. And we know exactly how long it takes for those elements to decay. So we can measure the amount of the parent and the amount of the daughter that element's decayed to. We know how long it's taken. So with the relative proportions of the parent and the daughter, we can measure absolute time.
So you're saying that we're literally using atomic clocks inside of rocks to measure time?
That's exactly right. Yeah.
Well, what do you say we dive into this and start looking at how those atomic clocks work? And then we can actually say how old, or how we figured out how old some of these things are.
That's exactly right. Let's do that. And so one more thing before we go on is I just wanted to bring to everybody's attention that while today's Rockin' Pop-Up is going to be about the events themselves and how we know how old those events are, we're also going to sprinkle in a little bit of the scientific history. Who are the scientists looking at these sort of questions, and how did they figure it all out? Sound good, Graham?
A double history lesson, geologic and scientific. I love it.
That sounds great. Okay. So, Graham, we're going to start off with the youngest of events, and we're going to go all the way back to the beginning of the Earth. So let's talk about the Pleistocene. What's going on there?
Ooh, the Pleistocene. It's a chilly time. Not quite as chilly as the Cryogenian behind me, but you can see in that picture over on the left, you've got this big white spot over Canada, and it's all the way out to Greenland, and it's covering up northern Wisconsin and Minnesota. And that's all ice during the ice age climates of the Pleistocene. And so we're not covering the whole globe in ice, but we're covering a bunch of North America. All these places that today are prairies and forests, they're under a mile or more of ice. And so in order to track time, we need isotopes that are able to measure, when things were, or I guess a better way to put this is ice covers up life. Ice makes it really hard for plants to grow. But plants, they take in things like carbon, and a lot of folks have heard of radiocarbon or carbon dating they may have heard of. Gavin, take us through carbon dating, because that's been really important for us to measure time in, at least in the most recent ice age climates.
That's right, yeah. So carbon dating is this crazy process where you have cosmic rays entering the Earth's atmosphere. And there are some types of elements or atoms that are in the atmosphere, and they get hit by these rays, and they turn into a specific isotope of carbon, a mass of carbon called carbon-14. And that carbon is then incorporated into plants via photosynthesis. So photosynthesis or photosynthesizing plants are taking in this carbon that's being made by cosmic rays, and they only take it in while they're alive. Then animals also eat the plants, and so while they're alive, they're also taking in this carbon-14. When these organisms die, they no longer take in carbon-14, and you start the clock for carbon dating. So this is a method for which we can measure when something was alive and when it last took in carbon-14.
Very cool. And to make these measurements, you need this jumbo machine that we've got down at the bottom of the screen here, that's called an accelerator mass spectrometer. There's very, very little of this carbon. So we need a big, powerful chemical analyzing machine like this in order to make these really, really tough measurements of these really, really trace amounts of carbon. And to dash in a little bit of that scientific history, a scientist named Willard Libby was one of the creators of carbon dating and a Nobel Prize winner for that achievement and that contribution to science.
That's right,
and to this day, carbon dating is really important for not only geologic histories, but also archaeological histories as well, keeping track of human timescales.
Yeah. And so as you can see on this left map, we have a bunch of red dots all along the outside of this ice sheet. And so the way scientists have used carbon dates to date this is that they go to where they think the periphery of the ice sheet would be at some time. And they measure a bunch of carbon dates to see how old all of those plants were and when they died. And they basically compile a bunch of these different ages and say, well, all of those ages are falling into this sort of window of time. So the ice sheet must have retreated back past that window of time when these plants were alive. And so that's a way of knowing, like, okay, this is when the ice sheet was retreated from this area. And so they build a record like that. So they're using absolute ages, but it's in a sort of relative way, right, Graham? Would you agree with that?
That's right. They're pacing it out, step by step through time. Whew. Gee, that sounds like a lot of work to me.
Yeah, I think so. These are pretty diligent people. So what do you say we go on to the next event?
Well, I'm ready. We've cooled down. Let's warm up with a little mass extinction.
Oh, the first mass extinction. Well, not the first, but the one that's, I would say, most popular. That's the KPG, otherwise known as the KT boundary. And this one is the one that killed the dinosaurs, right, Graham?
That's right. And there's two things going on here. One of them is many of us have heard of this Chicxulub meteorite impact. And so it was actually a father and a son, a physicist and a geologist, who sort of caught up the first evidence of this impact. And that was by them measuring a very rare element that you really only find in meteorites. It does exist on Earth, but it's actually been stored away in our core. Long story behind that. But the way we get this element to Earth is through meteorites. And Gavin, what is that special element?
Well, Graham, that element is called iridium. And so these guys kind of did something like a relative dating scheme. They knew how old the rocks were, but they pointed to a spot in the rock record. And they said, wow, this spot has really high iridium. So this is a graph of what one of their plots would look like. And so we have time on the y-axis and iridium on the x-axis. And when you hit that boundary, you get this spike in iridium. And so they were like, wow, this not only is an area where we think that a mass extinction may have occurred because we have dinosaur fossils below it and no fossils above it, but we also know that a meteorite impact happened there because we have an iridium spike. So voila, it must have been a meteorite that killed the dinosaurs. But Graham, is that the whole story?
Not so fast, because this meteorite came in the middle of this period of intense volcanic activity in what is today India. And this gentleman over on the right-hand side, Blair Shaney, who is a professor at Princeton, has recently been doing a lot of work studying the ages of when those volcanoes were erupting. And so we talk about, what made the dinosaurs go extinct. And this is still really an active scientific debate. People are still writing papers and making measurements and trying to figure this out today, when exactly the impact was and when exactly these volcanoes were erupting. And right now, the evidence suggests that these volcanoes were making Earth a very tough place to live even before that meteorite came. So, this extinction is kind of a bad plus bad time to be around. And so to date those, they're making measurements in these little minerals that are especially good atomic clocks called zircons. And those have been used for another mass extinction, right, Gav?
That's right. And so we have the KT boundary mass extinction, but let's go to the biggest mass extinction ever. And that is the Permian-Triassic mass extinction. This is the one that killed over 90% of all life on Earth. And so, funny enough, we don't have a meteorite impact, but we do have a lot of volcanoes similar to the Deccan traps in India, but this time they're happening in the Siberian traps in, Siberia. and so, Graham, can you take us through a little bit of how this goes? What is this figure showing us, and how are these guys doing it?
Yeah, so a scientist named Seth Burgess, who actually he works at the California Volcano Observatory now and lives in Santa Cruz. So that's kind of a fun connection there. But he collected some of these volcanic rocks from Siberia, and he made measurements on their ages. And he found that by really looking at these things closely, there were these different periods of erupting where these volcanoes were really active, and a lot of lava was erupted first, and then these things started baking a bunch of old rocks and releasing a bunch of greenhouse gases. And we know that greenhouse gases can make the climate on Earth really challenging to live in. And that's exactly what happened. So as these volcanoes sort of spread underground, they ended up baking the interior of the crust and releasing a lot of these greenhouse gases that heat up the Earth and made it really, really hard to live on, and drove these mass extinctions.
That's right, Graham. That's right. So these two guys, Sam Baring was Seth Burgess's advisor at the time. They went to India and they did a really nice study, and this is a map view of the area they looked at. They picked rocks from all around, and they got really precise ages with a mass spectrometer that's pictured here. They were dating, as you said, those little zircon minerals. So they got really precise ages and figured out just what you said, that the main mass of lava happened around 251.9 million years ago. But then all of these sort of swarms of lava that cover a larger area, those happened within 251.9 to 251.5. And it was those that sort of would have driven the greenhouse gases, which would have made the extinction more severe. And so you could see that, 251.9 to 251.5, those are pretty precise ages. So it takes diligent work and a lot of geologic prowess to map an area like this and get an age on it that means something in terms of like the mass extinction itself, right?
That's right. Yeah. And these folks are, we're really pushing the boundaries of, just how precise can we get those measurements? How good of a date can we get? And it's tough work.
That's right.
Cool.
Okay. So we talked about mass extinctions. Now let's go to where you are. We got to talk about Snowball Earth, right?
That's
You're stuck
right.
there.
Into the cryogenian. And, for the last 100 years, folks have recognized that there were these major glaciations on Earth. But it wasn't until about 20 years ago when Hoffman and Schrag, these two folks standing next to a lovely rock outcrop, really started to piece together and think about where continents used to be on Earth, and where they saw all this old glacial, these rocks that formed in a glaciated environment. They're realizing that glaciers weren't just up near the poles. They just weren't in places like Greenland is now or Antarctica is now. There were glaciers even down at the equator. So places like California would have been glaciated. Places like Florida would have been glaciated. The warmest, most steamy places on Earth would have been covered with ice that was wrapping the globe. And so it was important to recognize that. And so they used a bunch of things, including both looking at relative ages, looking at absolute ages, and then also using cool chemical tracers to suss out just what this world might have looked like.
That's right, Graham. And I'm glad you said that, because a lot of people might have already noticed that are watching this rocket pop up, that these papers, these studies that we're talking about are happening anywhere from the 80s to now. But really, these ideas have been around. And as the technology shifts and we get better and better at measuring time in the rock record, we can start really actually saying exactly what happened. We can get more specific about the Earth's timeline. And so we're really in a fun era to do that in. And so that's exactly what Hoffman and Schrag did. They took an idea that started in the 1850s or 1860s, and they reignited interest in it because they were like, hey, we have these rocks in Namibia, which is this big section here, and those look like glaciated rocks. And right above the glaciated rocks, we have rocks that look like they would occur after you melted a bunch of glaciers. And as you said, they used some chemical tracers. They're not exactly to find the dates, but to find some evidence for glaciation. And so that's actually a relative time study, right, Graham?
That's right. Yeah, and they're looking at where things are above and below one another to try and recreate these histories of environmental change on the Earth happening not anytime recently, 700 million years ago.
That's right. A really, really interesting time in Earth's history. It's tough to get into a Snowball Earth, and it's really hard to get out of it once you're in it. They actually figured out that in order to collapse a Snowball Earth and to start melting back that ice, you have to have some really big volcanoes, similar to the ones that caused the mass extinctions we just talked about.
Cool, Gav. So we've gone from warm to cold. Let's go back to a time when life was just first starting out. So here they're actually kind of keeping track of environmental change by looking at how, these chemical traces are responding to life. But we can go back and use those same sorts of isotopes of carbon that track the activity of life on Earth to actually figure out what life was like when it was just starting up here on Earth. That's
right, Graham. And so to remind the audience now, we've gone from 720 million years to 3.5 billion. So that corresponds to a shift between 10 p.m. and 4 a.m. So we're at 4 a.m. now. We've gone way back in time. And what we're showing here are the results of a study that was done in 2018. And this is some futuristic science, Graham, wouldn't you say?
I would say they've got this huge machine here. It's as big, or maybe even bigger than that one that they're using to date the carbon. But here, they're making these tiny little holes in this rock. And when I say tiny, I mean like 1/30th the width of a human hair. So you take out a hair, cut it into 30, slice it up into 30 pieces along the length of it. And then just one of those is how big these teeny tiny holes are. And they're able to make a chemical measurement of something that small.
That's right. Yeah. So they're taking this measurement, as you said, very small, and they're measuring these little fossils. These are the oldest fossils ever known. And it's really a relative age study because they're in these rocks that have been known for a while. The study was done in 2018, but the rocks were discovered in the 70s. And so these little fossils they're looking at are they're in 3.5 billion year old rocks. So relative dating would say, okay, they must be at least as old as 3.5 billion. And what they're doing is they're actually starting to chemically characterize them. And the results of this study show that indeed these are fossilized microbes, and they're actually very, very similar to microbes that are still alive today. So I just have to take my hat off to life. Life is lasting the whole day, the whole 3.5 billion years. And these really smart scientists from UCLA are able to measure it even 3.5 billion years later.
That's pretty cool, Gavin. And so we've got some really cutting edge science here. And instruments like this one that we see here are still being used today to go even further back in time and learn about the very dawn of our solar system when the Earth itself just began to form. But when we talk about that story, it actually, the first time we really got a good sense of how old the Earth was was in the 1950s, which is actually, that was a pretty good while ago for a lot of this geochronology, this measurement of geologic time. And a person named Claire Patterson and a colleague of his, George Tilton, were studying meteorites. And they were trying to use meteorites to understand the age of the Earth. And why would we use meteorites, Gavin, when they're not even from Earth?
Well, Graham, these guys had a really, really cool idea that meteorites probably give you the age of the solar system, when the solar system formed. And so Earth must have been pretty close behind, because as we know, when you're forming the solar system through the act of accretion, you are bringing a bunch of rocks together and you're making your planets. And so these guys were thinking, okay, let's use the isotopes of uranium and lead to date the age of meteorites. And so they made this chemical plot here, and we won't get into the details because it's pretty heavy into the chemistry and math side of things. But what they found was that this meteorite here from Arizona called Cadmium Diablo, it's the one that made Meteor Crater in Arizona, is the most primitive meteorite ever found. And
primitive, Gavin, that's a word. What does that word mean? What do we say when we say that a meteorite is primitive?
Good question, Graham. Thanks for catching me on jargon.
Oh yeah, right? No worries.
Primitive meaning that it's the least mature. It's the oldest meteorite we found. Would you agree, Graham?
I would agree. That makes sense. So when we say it's really primitive, we mean it's coming from a really early time. So the Earth, where we have plate tectonics and volcanoes and mountain building, those rocks aren't very primitive compared to Canyon Diablo, are they?
No, not at all. We don't have any rocks on Earth that are as old as Canyon Diablo.
Cool.
That's right.
All right.
Go on, Graham.
Oh yeah. So what they do is they're looking at the isotopes of lead in that meteorite, and they're using it to determine the age of these meteorites. And if we know about how old the meteorites are, we know how old the Earth is. And so that's a cool use of lead. What else with lead did Claire Patterson go on to do after he checked the box on measuring the age of the Earth?
Well, how do you follow up being the first person to know the age of the Earth, Graham? Well, Claire Patterson figured out a way to make the Earth a much safer place to live. And that's because when he was measuring lead in his samples, he realized that there is a ridiculous amount of lead in the atmosphere. There's just very unnatural amounts of lead in the atmosphere. And he figured out that it was lead in gasoline that was being burned and being introduced into the atmosphere and actually poisoning people. So we know that lead is very toxic to humans, and the level of lead was enough that people were actually going crazy and dying because of it. Right, Graham?
Yeah, so he went on to recognize, a really important environmental issue with lead contamination in gasoline. And so that's why today we have unleaded gas. We can thank Claire Patterson, along with some other really, active folks who helped make this world a safer place by cleaning up our gas.
That's right. So we've done it. We've gone all the way back to 4.5 billion years and the start of the Earth.
What a journey.
Next week, Graham?
So next week, we're going to do an interview with the gents. We're gonna talk to two scientists who each of us know respectively pretty well and learn a little bit about what it's like in a day of a life of a geologist.
That's right. If the audience wants to know what we do on a daily basis and how we actually do science, that's what we're going to be talking about next week. So stay tuned for that.
Cool. So it sounds like we're going to be jumping from the scientists of the past couple decades, past century, and next week looking into the scientists of today. Is that true?
That's right.
Awesome. Great. Let's stop that. So I have a question about the oldest rocks part that we just kind of finished on, because you ended up with talking about meteorites and that being our ability to date how old the Earth is, when the Earth formed. But did you mention like what the oldest rocks on Earth are? Like, is that what we would call the oldest rocks on Earth? But they weren't like part of the Earth forming. They were placed here after the Earth formed, right? So do we have any sense of what the oldest Earth formed rocks are?
We do. And so there's two parts of the question. There's the oldest minerals ever found and the oldest rocks ever found. I'll take the minerals and Graham can take the rocks. So the oldest Earth formed anything ever are the oldest Earth formed minerals. And those are zircons, the ones similar to the ones we talked about today from Australia. And those were called the Jack Hills zircons. And those are around 4.2 billion years. So those formed in the lavas that are similar to the ones that are behind me right now, 4.2 billion year old zircons, but they're probably reworked. The reason that the rocks they're in aren't the oldest rocks is because sometimes the zircons survive, but the original rocks they're in don't. And so those were probably formed in 4.2 billion year old rocks, but now they're in younger rocks. So
cool. Yeah. That makes sense. That's interesting.
Yeah. So those are little grains in these sandstones that are far younger than the grains that make them up are.
Exactly.
But if we want to take a rock where we can go find it on the Earth and hold it in our hand and say, this rock is the oldest rock on Earth, there are two candidates. The one that's most widely accepted are the Acastonices. They're these ancient metamorphic rocks up in northwestern Canada, and those formed 3.8 billion years ago, right around that period of time. There are some rocks in Greenland that are contenders to being around that age to a little bit older, but Greenland and northern Canada are where some of the oldest rocks on Earth can be found.
Is that something that like certain scientists, that's what they're after? They're just looking for more and more samples to figure out, like they're hoping to find the oldest rock, or is it something that you stumble upon while working on other projects?
I think it used to be something that folks were really chasing after. Now it's more of a, if you find it, that's very exciting. But I think for the most part, geologists feel like we have a decent sense of how old rocks on Earth are, with some exceptions.
Cool. Okay. Well, I'm really looking forward to learning more about the work that scientists do next week and getting a taste today with some of the tools that you all employ and that scientists have been employing for some of these really, really large discoveries, and learning about what's going on today in the lab. So that's going to be fun. Can't wait for next week.
Nor can we.
Okay, great. So we'll see y'all watching at home next week. Again, if you have a rock you want identified, you can send us a picture. Details are in the description. We'll see you then.